In this lecture, I would like to first prove the following proposition. So suppose we have a collection of sigma algebra. So let's suppose you have a collection, let's say B lambda. So here lambda coming from some index set, let's use capital lambda. This index set can be really large. It doesn't have to be countable at all. It's just a collection of sigma algebras. They're on some same space X, of course. Then I want to show the following, the intersection of all of these B lambda. That's going to be a sigma algebra. So basically the intersection of sigma algebras are again sigma algebra. So how to prove something is a sigma algebra? Well, we just need to go through the three definitions. So first of all is the empty set in there. Well, you know empty set is in each of these B lambda for all lambda. So it's certainly in all of them. So the empty set is inside this intersection. Is it closed undertaking complement? Well, you take any set A inside this intersection, lambda in lambda of B lambda. Well, what does it mean by a set A to be inside the intersection? Well, it really means it's inside every one of them. So A is inside B of lambda for all lambda. This is what it means. But you know B lambda is a sigma algebra, so it's closed undertaking complement. So the complement of this is also inside B lambda, again, for all lambda. So because this complement of A is in all the B lambda, well, it certainly is inside their intersection by the definition of intersection. So this X takes away A is contained in all of them. So it's contained in the intersection. So this shows that this intersection is closed undertaking complement. And you can probably write the same proof for countable union. So let's just say take an where n going from 1 to infinity, there are some sequence of sets inside this intersection. And you can convince yourself their union, their countable union, this an, is also inside this intersection. So this, I'll leave it as an exercise. It's essentially the same proof as the second point. You just do this for each one of them and you take their intersection. All right, so basically we now show that the intersection of any collection of sigma algebra is again a sigma algebra. So now we want to introduce a really important notion called the sigma algebra generated by a set. So here is our definition. So let's let F to be a collection of sets. So let's say is contained in power set of X. Okay, so it's a collection of sets. F itself may not be an algebra or a sigma algebra, it's just some collection of sets. But we want to find some sigma algebra that's kind of generated by F. What do I mean by that? Well, here is the definition. So let's define the sigma algebra generated by F. To be the following. Okay, so first of all, let's use the notation sigma of F to denote the sigma algebra. To say this is the intersection of all the sigma algebra B lambda. Okay, so here this collection B lambda are all the sigma algebra containing the set F. So basically, if you just consider all the sigma algebra on X, and you pick out those sigma algebra that containing your set F, then you get your collection B lambda. Now you take the intersection of these B lambda, you get something what we call the sigma algebra generated by F. Of course, here we need to show, first of all, this definition is well defined. We're not defining something stupid. So first, I need to show that this intersection really makes sense. So why can it not make sense? Well, when you take the intersection, you always need to be careful. You want to take intersection over a non-trivial collection of sets. So you don't want to take intersection over nothing. So to show that you're not really taking intersection over nothing, you really need to show that there has to exist some sigma algebra containing F. Well, this one is clear. Well, the reason is there is a sigma algebra, namely the biggest one, which is the power set of X. That's a sigma algebra. We already shown in the last lecture. So we have a sigma algebra containing F, so this intersection makes sense. So we're really not taking intersection over a empty set, basically. All right. And second, why this is called a sigma algebra generated by F? Well, we need to show that this is indeed a sigma algebra. Well, we just prove a proposition. So now, since each of these B lambda are sigma algebra, then we show the intersection of sigma algebra is again a sigma algebra. So that tells us that the intersection of these B lambda is a sigma algebra. So this sigma of F, which by definition is this intersection, is indeed a sigma algebra. Okay, so we're saying this is a sigma algebra, but now we know it's indeed a sigma algebra. And I want to claim that this sigma algebra is very nice in terms of it's actually the smallest sigma algebra containing F. So here's the proposition. So sigma of F is the what we call smallest. I'll explain what I mean by smallest later. So it's the smallest sigma algebra containing the set F. So we're pure mathematicians. We cannot just say what smallest without explaining. So by smallest, what does it mean by smallest is that the following. So if you have a sigma algebra B, that's a sigma algebra, and suppose B contains F, so F is containing B, then being the smallest sigma algebra means sigma of F should be a smaller sigma algebra compared to B, and when you compare two sets, smaller means one is contained in the other. So this will imply the sigma of F is contained in B. So this is the property of the sigma algebra generated by F. Is the smallest. It has to be contained in any sigma algebra containing F. The proof is fairly simple. Well, by definition, this sigma of F is really the intersection of a bunch of sigma algebra. So sigma of F, by definition, is the intersection of all these sigma algebra containing F. And because B is a sigma algebra contains F, okay, so sigma algebra B contains F, that will imply that B is one of the B lambda, okay? Because B lambda are all the sigma algebras containing F, and B is one of them. So B is one of the B lambda. And the intersection is certainly contained in a single one, so maybe let's use B lambda not, just to differ from the generic element. So this intersection is certainly contained in this one particular B, so this is B. So in other words, the sigma algebra generated by F is smaller compared to B, is the smallest. All right, now we clarify this notion of a sigma algebra generated by a set. This is going to be a really important concept. We'll see this a lot eventually. Let's just talk about one such sigma algebra generated by a collection of sets that we're going to see quite often in this course is called the Borel sigma algebra. So here, let's go over the Borel sigma algebra. So for Borel sigma algebra, we need to start with a metric space. So let X be a metric space. So here the metric space is a generic one. You learned it from PMATH 351. Once you have a metric on the space, now you can define what does it mean by open and closed. So you can now define, let's let G to be all the subsets of X where it's open. So here the openness comes from the metric. Well, then we define, so here's the definition. The Borel sigma algebra on X is basically the sigma algebra generated by the set of open sets. So let's denote this because it's an important one. Let's give it a name. So let's denote it by a Borel. So let's use B, and then I use X. So to denote, we're really talking about this metric space X. When X is clear, then we can just ignore the X and write B if the context is clear. But otherwise, let's keep the X in the subscript. So this is the definition of a Borel sigma algebra. And Borel sigma algebra is very natural because it contains the open set. For example, on the real line, when you want to define a measure, you usually first define it on open intervals. And then you consider the smallest algebra that makes these open intervals measurable, then you get a Borel sigma algebra. You may already learn it from PMATH 450 that Borel sigma algebra on the real line is not a Lebesgue measurable set, which is a sigma algebra. We're going to see that eventually, but Borel sigma algebra is slightly smaller than the Lebesgue measurable sets, so they're different. All right, so just want to clarify a bunch of notations. So here we usually use G to denote the set of open sets. And we use letter F to denote the set of closed sets. And you've probably seen this notation before, the G delta. The delta means intersection, so it's really the countable intersection of sets from G, so it's the intersections of AN, where AN is in G, so it's open. And sometimes we also have the corresponding one for closed set. So when you take the union, so F sigma, so sigma means countable union, just like in the sigma algebra. So it's the countable union of AN where AN are closed. In other words, they are coming from F. And it's very clear that these G delta and F sigma sets, they are also Borel. So we know that G delta, F sigma are both in Borel sets. So they're both Borel of X. All right. And we also want to define some notions. So let's call a set A containing X is called Borel if it is inside the Borel sigma algebra, if A is an element of the Borel sigma algebra. And what kind of sets are Borel? Well, there are trivial ones. So for example, open sets are clearly Borel because they are in the open sets which generate the Borel sigma algebra. Closed sets are Borel because they are the complement of open set. Remember, in the metric space, closed set means its complement is open. And Borel sigma algebra contain all the open sets will also contain the complement of open sets, which are closed sets. So all the closed sets are Borel. And we saw that G delta sets, F sigma sets, they are all Borel. And this list just goes on. And for example, if x is equals to the real line with the usual metric, the usual distance, you can show that, for example, the half-open intervals, they're all brown. So they're all in brown of x. And in fact, you can show many sets you know they are brown. So it really contains a large collection of sets. And that's why this is a very useful sigma algebra that we'll see a lot in this course.